Spatial inhomogeneities in a holographic superconductor.
Okay. I would like to thank the organizers for inviting me. And I will introduce our recent work on the thermal quenches induce the spatial inhomogeneities in holographic superconductors. This work was collaborated with Antonio Garcia and Hongbao Zhang. Actually, our main result was that we have obtained spontaneously invariant symmetry breaking in the holographic superconductors, although the initial state and the quench is translational invariance. So this is our main result. And before introducing our work, I will introduce some developments in the holographic superconductors. Okay. So first, I will introduce the static homogeneous holographic superconductors. And then I will introduce the dynamic homogeneous superconductors. And then I will introduce the static inhomogeneous holographic superconductors. Okay. For the static homogeneous superconductor, this means static means it's independent of time. And homogeneous means it is independent of the spatial direction. So in 2008, Gupta, Hanno, Herzog, and Horowitz, they have introduced the holographic model of the superconductor, I think. And they adopted the Einstein, Maxwell, and the complex scalar actions. And they found that if the temperature is greater than critical temperature, there are just only one trivial solution. It is the scalar field is vanishing. But when the temperature is lower than the critical temperature, there will be two available solutions. One is that the scalar field is zero. Another one is the scalar field is not zero. This solution actually is the superconducting solution. So by comparing the free energy, they found that the superconducting solution will have lower free energy. So this is thermodynamically favored. So this is more plausible for us. So this means when the temperature is lower than a critical temperature, they will find superconducting solutions. So next, I will introduce the dynamical homogeneous holographic superconductor after quench. Dynamic means, in this case, it will depend on the time. Okay, so this picture is accepted from the Murata's paper. In this paper, they have studied. They found that when the temperature is smaller, is lower than a critical temperature, and then the ADS black hole. This is a charged ADS black hole. After a Gaussian quench, they have quenched the scalar field in the bulk, and finally they found that the static hairy black holes, this kind of iron ADS black hole will develop to the static hairy black holes. So on the boundary, this means the normal phase after the quench, it will become the superconducting phases. Okay, so in the initial time, actually this is just the normal phase. This peak is due to the quench. And as time goes by, they find that the order parameter will go to a finite value. This means this is it's a superconducting phase. And then Bassin and Gonzalez, Simons and Sonner, Weissman, they also studied the non-equilibrium behaviors in the holographic superconductors. They have found 3 different kinds of oscillations, damping oscillations of these order parameters. Okay, let me see this first picture. You will see that there are some oscillatory dampings of the order parameter. And in this case, the final temperature is smaller than the T star. T star is a kind of a dynamical temperature scale in their paper. And the second one is if the final temperature is between the T star and the T critical temperature. Okay, this critical temperature is just the temperature of the phase from the normal phase to the superconducting phase. So in this region, they found just the damping of the order parameter. This means there are no oscillations. Okay, here there are oscillations. Here it's just the long oscillatory damping solutions. And after a long time, the order parameter will go to a finite value. This means when time is longer enough, it is in the superconducting phase. And in the third region, the temperature, final temperature is bigger than the TC. They found just the damping solution, but in this case, the order parameter will go to the will be vanishing. So this is this system will go to normal phase. And also, they also studied the quaternion modes in this system, and they found that the quaternion modes analysis is quantitatively consistent with the pictures of the order parameter. And okay, actually, these two papers, they studied in the black hole background. So because there will be a horizon in the bulk, so all the fields will be finally absorbed by the horizon. But in this paper, my collaborators Gao Xingao and Antonio Garcia and Zhenhua Bi, and we studied the time evolutions of the holographic superconductor in Edison space-time. Because in Edison space-time, there's no horizon, so no fields will be absorbed by the horizon. So it's like just like a box, and the wave will go left and then hit the wall, and then just will go right again. So here, as time goes by, the order parameter will just oscillatory with the time. So we also found that this kind of just low damping oscillatory of the order parameters. So in the CFT or in the condensed matter series, this is very similar to the lack of the thermalization. This means on the boundary, maybe the field theory is not thermalized. So then from the condensed matter theory, people always say that the lack of thermalization is related to the integrabilities of the system. So a lateral question is, what's the relation between a gravity without horizon, okay, such as the Edison, and the relation between this gravity without horizon and the integrable field theory on the boundary? So I don't know. So because this is this question is raised from our numerical results.
This behavior is due to your system has a gap, right? It's not due to whether.
Actually, the gap is also because Edison also has a gap.
Yeah. So here the lack of thermalization should be related to have a gap, not due to integrability.
Okay.
Yeah, you have to have gap, then nothing to thermalize.
But from this paper, I read it, and okay, I don't know. Maybe you're right. Okay, next, I will introduce some static inhomogeneous studies of the holographic superconductor. Okay, in this case, static means it's independent of time. Inhomogeneous means it's it will depend on these spatial directions. Okay, this is This is the Flogger and his collaborators' paper. In this paper, they have introduced the Einstein-Maxwell scalar actions, but they have explicitly introduced the modulated chemical potential. I mean, explicitly means it's not, how to say, on the boundary they have periodic chemical potential put by hand. So, I mean, and then they found a kind of striped order parameters. And okay, this will break the translational symmetries. And also, they found that the free energy of this kind of inhomogeneous solution is lower than the homogeneous case. And so, the importance is that the Donners and Gauntlet and Rosali et al. I think maybe Rosali tomorrow will talk about this again. Okay. They found that they have introduced Einstein and Maxwell axion actions. Okay, the importance actually here is the axion action. And they found that this kind of action will spontaneously break the translational symmetry. This means this kind of translational symmetry of the system was spontaneously broken, not explicitly broken, like this one. So they also found this kind of striped order parameters. Okay, and also Honyu and Oguri and their collaborators, they also found that in the holographic setup, they found that the transimus terms can spontaneously generate the angular momentum. So in the following, I will also come back to these 3 papers because this is the motivations for our studies. Okay, there are also many other references, such as the Amadas and Matthias Kaminsky and Nancy Taylor. They have studied the quational modes of the holographic superconductor. This is a kind of dynamic studies. And also Bizon, this morning he has introduced his papers. And but in this paper, Basun, he also studied the non-equilibrium studies in the Edison space-time. And also here is the inhomogeneous studies. Horowitz yesterday has introduced this. And okay, I will talk about our motivations to study the dynamical and inhomogeneous holographic superconductors. Okay, actually in the kinetic matter field theory, there's a kind of Kibble-Direct mechanism. This mechanism states that if the initial state of the system has a higher symmetry, okay, maybe for instance, if the phase is randomly directed to every directions, so the initial state has a higher symmetry. But after a quench, okay, this quench can be, the temperature is cooling down by some reason. And after this quench, then there will be some topological defects. Maybe you can also call it as vacuum. So in every topological defect, the phase will be correlated. This means maybe the phase will be, okay, maybe I should, okay, in the initial case, initial state, the phase will randomly direct to every direction. So this has a higher order symmetry. So, and after the quench, there will be many topological defects maybe here and here. And in every topological defect, the phase will be correlated. They will direct to one direction, and here maybe it will direct to this direction. And so, but between these topological defects, there should exist some vortex. Vortex should exist. This is the Dirac's statement. So this is the general motivation for our study because the initial state is has a higher symmetry, and then after quench, the final state has less symmetry. And then I have said before that this is a direct experimental paper. In this paper, they say that study that if the system size is larger than the superconductors, and then after the quench actually will excite some finite momentums. So this kind of a finite momentum will result the spatial inhomogeneous. So this is the direct motivation to our study. And also in the holographic, from the holographic aspect, I have said that Adonis and Rosani and whole newspaper, they also studied that if they introduce axion fields or the Chern-Simons terms, there will be the translational symmetry will be break, and angular momentum will be automatically generated. So we want to ask how about the quench, and depending on the time. So is it will break the translational symmetry? Okay, so our answer is positive. We come to our studies. Okay, in this work we have introduced the Einstein, Maxwell, and the scalar fields. But in this case, and also we adopt the ADS Schwarz black holes. But in this case, all the fields should be depend on the time and the radial direction in the bulk and x direction. X direction is a direction on the spatial on the boundary. Okay, this seems very complicated, but we use the Chebyshev spectrum method to study it. And the answer is that the scalar field, this rho is the density of the scalar field. This phi is the phase of the scalar field. And this mi, I is t, r, and x. Mi is the gauge invariant quantity. And we found that the phi actually will be automatically absorbed in the equations of motions. So finally, we found 4 independent equations of motion for the mi and the rho, and 1 constraint equations. Okay, and then the boundary condition is that at the horizon, the time direction, a time component of the m is imposed to 0. Okay, this is the same as before. And other fields at the horizon will be finite. And for a simple case, we choose the m squared is minus 2 over L. Okay, we have choose L. L is equal 1 here. And the expansions of the fields near the boundary is like this. Okay, here. The rho star is the charge densities, mu is the chemical potential, and the source, rho 1, this one we will impose it to be 0. And the order parameter is the rho 2. And v, here v is just the superfluid velocity. And because we don't want to have some current along the x direction, so we have imposed the j current be 0. Okay, our thermal quench is because temperature is a proportion to 1 over mu. So if we want to quench the temperature, it is equal to quench the chemical potentials. So the quench A is that the initial chemical potential is 4.5. Okay, it's bigger than the critical chemical potentials because from this paper we know that for m squared is minus 2. The critical chemical potential is around 4. So the initial state is also a superconductor. And the final chemical potential is bigger than this one. So this corresponding to that the initial temperature is around 0.9, and the final temperature is around the 0.85. Okay. So this is the chemical potential, and this is the order parameter. We found that after the quench, you can see that along the x direction, the order parameter is inhomogeneous. So this kind of inhomogeneity is automatically generated because the initial state is homogeneous and the quench is also homogeneous. So physically, this means because the quench has some energy, this energy will excite some finite momentums. So this will generate the inhomogeneities along the x directions.
What is driving the quench? Is it mu, the chemical potential?
The mu is put by hand.
So why do you say it doesn't look homogeneous?
You mean here?
Yeah.
Because this is the peak. So we use the spectrum method. Sometimes if the peak is too narrow, and then the picture is, how to say, is not that good. Because the peak is too narrow. So it looks like it's not homogeneous. So actually it's homogeneous because we have checked the precisions in the codes. The precision is maybe 10 to minus 5.
I don't understand. I mean, are your initial conditions truly homogeneous?
Yeah, yes.
Then how are you not having equally homogeneous final conditions with classical evolution?
Because actually we also compare the free energy. We found that the inhomogeneous free energy is lower.
You're not doing quantum statistical mechanics. You're doing classical dynamics, right?
Round off errors.
Yeah. Yes, in the
But
gravity.
it's instability. There could be instability to go into say finite momentum mode.
Yeah,
You
of
will
course.
go there.
Okay, so if you're saying the initial conditions is merely homogeneous plus noise, that's a different
Okay,
answer.
yeah, of course, you want to twist a little bit, yeah, but of course, in the end, it's just a reflection of conservation of momentum. So you do a quench and the system can decide to excite a little bit in momentum and then it becomes homogeneous. This is completely...
But are there any
But the system, there's no system decides to excite here. That's like
No,
quantum
it's like what
language.
he said about the Kiefer-Surek mechanism. So you start with something homogeneous, of course, with some noise, so the system
So
can
you-
go from some homogeneous to inhomogeneous solution.
You put noise in by hand.
No, I mean, you don't have... it's not...
We put the chemical potential by
Yeah.
hand. I think that
But you put in some spatially
Yeah,
fluctuations
something-
that are small.
yeah,
by
something,
hand.
yeah, and then you see some big effect.
Yeah, you put a seed, then
Yeah.
they will
Yes.
grow.
That was the
Yeah.
question.
Yeah, otherwise, if it's identical,
Can I
to
ask
zero,
a
then
simpler
it's
question?
identical
Yeah,
to
if it's
zero.
identically zero, zero, you cannot go.
Is your boundary condition that you keep mu constant for a while and then at one time you drop it to a lower value and then keep it constant?
you mean the reverse, either reverse direction.
Or you keep it high and then you drop it? I mean, you
No,
want
no, no. I will give a lower, and then we give. Finally, the chemical potential is higher than the initial.
No, we just impose boundary condition for later time to be some, the chemical potential to be the mu final.
I mean, I'm puzzled because your plot looks like mu is oscillating.
No, but this is just for very short times. This is just the quench. The oscillation in mu is the quench.
But I thought mu is fixed. Mu is input.
No, I mean, it's fixed, but you need just to change it numerically. You have to give some room. You cannot change abruptly, completely from mu initial to mu final. So you have to give some for short times. So then you see that for longer times is constant. And then you see that the space generation occurs for longer times. So what is important here, forget about the short times, forget about that. What is important here is that for longer times, mu is constant, and you see the space generation. I mean, you see the gap is especially inhomogeneous. This is what is relevant. The other is technical thing that you have to do the quench.
Okay, thank you. And here you can find that the order there are five. There are four curves here. So this is these curves that are exported from the different directions. Okay, this is from the x equals 0 and x equals 4 because we do it in the finite widths. And here this is x maybe is 2 and here x is 3. And from the right picture is from the bottom to the top. This is the time. This is actually this is a homogeneous case. It's t equals 0. Here t is 1.2 and here t is bigger. And finally t is 30. We found that we can find that indeed the inhomogeneous will be enlarged.
Your expectation value is a function of both t and x?
The equation and motions are on x.
Your expectation value is
this
a
one?
function of both t and x?
You mean this picture?
I'm asking about the expectation value, not the picture. Is it a function of both t and x?
Yes.
So
T, R, and X. R
you're
is,
showing slices there
Yeah,
of this
yeah.
expectation value?
yeah. So here you can find that here the order parameter will oscillate in time, and this is the here is the inhomogeneous order parameters. And for the quench B, we have choose a larger initial chemical potential, and we found that the difference is that here in the intermediate time, the quench is just monotomically increase. It's different from this one because here there are some oscillations in time. But for the quench B, we found that it's just the monotomically increase in time. So we also okay.
At late times, are you arguing that that's an equilibrium configuration?
It's go to the steady state like this.
Is it time independent?
No time dependent. It's just a steady. Just depend on the x directions.
Did you try and construct that spatially modulated time independent equilibrium configuration directly?
Time dependent.
Independent.
Time independent modulate. Well, our quench is like this. This final chemical thing is a constant. So it's just a constant, not modulated chemical potential.
Yeah, so you could ask the question, if that is an equilibrium configuration, you should be able to construct it independent of the way you have constructed through your process.
Okay.
But I think for these parameters, there's no spatially modulated instability for this model.
Instability. But we
Horizon odds and black hole.
actually we have. Okay, you mean compared to the RNA black hole?
Well, the question is that you can go till you can go. I mean, this, what we can prove is that in this range of times, this configuration, they have lower energy than the homogeneous configuration.
Yeah,
I wouldn't make any claim about what happened for a very long time. I don't know.
But it's static. After your chemical, I mean, at least according to your figures, after the chemical potential has become static, after T is 10, it looks like it's a static solution. Now, if it's a static solution, it should solve the static equations, and one can wonder,
Yeah, but
what the solution is.
yeah, but then
We don't know. I don't know.
we check that these solutions they have lower free energy.
Yeah, but what is the solution itself? I mean, it's just odd that there's a static inhomogeneous solution at all.
I mean,
Yes.
the solution is this solution. I don't know what you mean. I mean,
I think this depends on the chemical potential you have chosen. We have chosen this kind of chemical potential after a long time, so it has this kind of behavior, inhomogeneous behavior.
yeah, you can prove, for instance, that the oscillation is more or less the correlation length of the superconductor, which is what you expect.
How many points do you have in x direction?
X direction.
Yeah, like how many?
40. You mean the grids we have
Yes.
chosen? 40.
40
Yeah.
in x.
Yeah, in X, because X is actually is 0 to 4 because it's in the X is symmetry, so we have -4 to 4. And also we also compare the free energy between this inhomogeneous solution and the homogeneous solution. We found that actually this difference is smaller than 0. So this kind of inhomogeneous solution is thermodynamically favored. Okay. The real energy.
Is it constant?
You mean the real energy? What's the real energy? Sorry.
The mass.
Mass. Mass is -2. I mean mass squared. So
Not the gravitational side, just the scalar field energy.
Sorry, you're not talking about the mass of the scalar, you're talking about the bulk energy when you integrate over the bulk.
Energy. Yeah. In the.
You're asking whether energy is conserved?
yeah. We didn't consider this.
But you don't have to, right?
Yeah, it won't be conserved.
The hacking is dependent this is a time-dependent process.
You
You start with some initial state that has some energy and some conserved charge.
Right.
You change the chemical potential.
Yeah, but
That doesn't actually change.
for the quench process, you put in the energy, right? If you want to do quench, you put in the energy.
If you just change the chemical potential, how is that doing work?
Okay, I suggest we just let him summarize.
Summarize is I have introduced the development in holographic superconductor, and I also introduced the motivation. It's the dynamic solution. Okay, thank you for your attention.
Oh, right. We had plenty of questions already, but maybe somebody else has one.
So at late times, these oscillations it didn't look periodic.
It's like a periodic. Yeah.
I'd like to clarify what your chemical potential, which is a source, does. So it changes with time between two constant values. It doesn't matter how.
Yeah.
And at the same time, you put inhomogeneities in the x direction.
No.
Is that correct?
No. The inhomogeneous is a spontaneous generator.
You see what is
It's
interesting?
the hydro. Yeah, it's the numerical solution. It's
It's not round down errors.
From the air.
It fix mu though, it's boundary conditions.
Yeah, I don't.
So there shouldn't be any round-up errors in mu if that's what you're fixing.
if you impose the partial of the derivative of the fields over the x is 0, of course you will get the homogeneous solution. We didn't impose this boundary condition, so we finally get the
Do you impose the quench by fixing mu at some initial time and mu at some final time and let it evolve freely in the middle? Or do you impose a step function?
Yes. Yes. In the intermediate time, we just relax this condition, boundary condition of chemical potential.
But mu is a prescribed function of time?
No.
No, mu I is constant. Mu F is also constant.
Yeah, but it is you that impose how mu changes with time as part of your boundary condition?
No.
No.
No,
Mu is
it's
the
just-
source,
it's
so
the
he
game.
has some random.
Mu is put by hand.
No.
But why does it change so abruptly?
No. You impose the boundary condition is you have some initial mu at t equal to 0, and then you say that at a later time you want solutions with a different mu.
Yeah, you let mu at the intermediate times be free.
What is the equation of motion for mu?
Yeah,
mu is the boundary.
It's a free parameter. You get to choose it.
Yeah, you
What?
choose it.
You get to choose it. You get to thank God with the chemical potential. No, that's
Why?
Okay, I suggest we keep some order. The next one was not here.
I wrote you an email about this, but maybe can maybe just give some insight into what fixes the period of your late time inhomogeneities? What does it depend on, that the periodicity?
I think the periodicity depending on the strength of the final chemical potential. For different quenches, the period I think is not different. It's different, not.
Like the duration of the quench? You mean?
The value of the quench. I mean the strength.
The amplitude.
Yeah. I mean the 5 and 5.8. I mean for different values of this mu I, this kind of periodicity is different.
No, this is the amplitude. The
you mean
oscillation, they are the same for all the points.
I think he asked the periodicity. Maybe.
I meant the periodicity, and I thought they are the same for your different quenches A, B.
Yeah, I mean this periodicity depends on the quench.
So final question by something.
Right, so it's just a related question. So if you have two scale mu I and mu f, then which is really relevant to the periodicity? Or both are relevant?
I think we didn't consider this. But, yeah. Okay. There was some relation, but we didn't consider it.
If it is, really periodic, you could do some variational calculation for those, which divides the
Okay. Because here we just from finite width. This is from -4 to 4. But if you extend it, and you will find that this actually is a kind of period of densities.
Okay, it's great to have loads of discussions, so thanks to everybody, and thanks to you.